sampling with unequal properties. Okay. So now we are want to discuss unequal property. So why? First question is why we care, right? Why we consider unequal property sampling? Here's a two example. So population of four companies, whether it's a company or a farm. So if it's a company, then the size means the number of employees. If it means farm, it could be acres. Okay, the size of farms. Okay, and then it makes sense to have yield proportional to roughly proportional to the size, right? The bigger land, the maybe you will have more yield. So let's consider two options. One is the with equal property. Other one is with property proportional to size. And then, so then equal property sampling, it means that we have a selection property 1 false, right? Or with the properties proportional to size is a with property. So this is a 1600. So that means 1 over 16, 2 over 16, 3 over 16, 10 over 16. Okay. And so then compare the variance. Okay. So then this one, the total. So what is the variance? Well, then the estimator, so T hat estimator on the simple and the sampling, or T hat PPS. Okay. So if you do simple and the sampling, you will get 11 times 4, 20 times 4, 24 times 4, 240 times 4. Because you're selecting only one. You're selecting only one. So then if you observe this one, then you will multiply by the inverse of the property, right? So that is is it right? So Hurwitz-Thompson estimator. Remember, Hurwitz-Thompson estimator is this one. And here we are talking about selecting one. Okay. Selecting one. And so and here pi is 1 over, right? This is a pi I. So this is a pi 1, pi 2, pi 3, pi 4. So basically this is an estimator. Hurwitz-Thompson estimator. Okay. The same way, the Hurwitz-Thompson estimator is times 16 over 1, 20 times 16 over 2, right? And is 24 times 16 over 3. And this is 24 times 16 over 10. Right? Because we divide yi by pi I. And this is pi I. Okay. So now that we have an estimator, right? Table of estimator with the probability, we can compute the variance. So So variance of simple random sampling on the simple random sampling, right? Is what? 1/4 times 11 times 4 minus this is what is the value? 0, 1, 1, 2, 4, 5, 0, 300, right? So 300 square. 20 times 4. So, okay, let's do it. 44 minus 300 square plus 80 times minus 300 square. 96 minus 300 square plus, wow, 200. So, um, 980 minus 300 square, right? Will be something. Something looks very large, right? You have a 980 minus 300 square, which will be quite large. Now let's take a look what would be the variance of PPS. Okay, so that in that case, this is 176 minus 300 times 1/16 plus yeah, so 160 minus 300 square times 2/16, right? And then 144 minus 316 times 300. I don't know whether this is really correct, but yeah. Anyway, something. So uh, 16 times 24 equal to 180. Three, so 300. Yeah, it's a little bit strange. Why? Okay, 205. Okay, 245. Okay, 245, which is even, yeah. So I think it's okay. Yeah, two. Let me studio. We should yeah, okay. 245 times 16/10. 390, right? Minus 300 times 10/16. Okay. Something like that, right? So, oops. Uh, so, yeah. So you can see that if you look at we haven't really computed the variance, but the variance will be much lower here because, yeah, what should we? Okay, maybe we can let's compute. So 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 if you do that, right? Uh, then is you get one oh, one. Okay, this is the value of variance. While second one is 76 hundred square divided by 16. Right? Second one, so if you do use equal probability simple random sampling, you get 104K, 54K. If you do that, 13 to 64. So roughly 13K. Oops. Sorry. Okay. So here's a result. Okay. So variance is much smaller, basically. It's not surprising, right? We So that means this is a typical example of why BPS sampling or unequal part sampling is better uh, than simple random sampling. Okay. This is another example that that is kind of interesting and important actually. So suppose you have a small town. Okay, so this is a small town, and then you are interested in estimating the percent of families owning home. Okay, so you are interested in estimating this one, but you have your sampling frame happen to be school. Okay, so you have access to the school children. So you can ask the students, students about whether you have a house, you own the house or are renting it. Okay, so then the reporting unit is school children, but the analysis unit, what do you mean by that? That means that the definition of parameter theta. Okay, so the definition of parameter. So the parameter of interest is the percent, right? Probability of. So if you define this way, so one is the own, zero is right, not owned. Then the unit is what? Family. Okay, family. So the reporting unit is children, but the analysis unit is family. But they have a different implication. Why? Okay, so what is the theta in this population? So among the families, so the total number of family is 5,000. 50,000, right? And so among 50,000, we got 21,500 families owing home. Okay, so the parameter is this one. This is a true value. We are not talking about sampling at this point. You just, suppose we ask all the students, okay? So suppose we collect the data in the family level, then we investigate the 5,000 families, right? And then among them, we get 40% owing home. Okay. But because of the distribution, okay, so turns out that among the this is not exactly correct. Okay. So what do I mean by that? Okay. I think number. So how do you get this one? 500, 5,000 times 4. Okay. We have a 5,000 family with four children. Okay, 4 children. So then in terms of the children level, we have a 20K. Okay, so this number is derived. You can basically multiply this one to get this one. Okay, and here you have a 3 times 10,000 to get 30,000. Okay, and 2 times 15,000 to get 30,000. 1 times 2,000 and 20,000. Okay. And in each group, we'll have the same, right? The percent. I think the last column is incorrect. So the percent is so 10%. Okay. So among 2,000, we have what? I think this part is not correct. So because we have 20 children, they have 10% renting, owning the house. So then in terms of the children level, we get 2,000. Okay. How about here? 30,000 times 30%. So then 9,000, right? I'm talking about the number of children owing home. Do I? Okay. Owing home. Okay. So among the 2,000, 20,000, we got 2,000. 30,000. Okay. 9, right? 3 times 3, 9,000. This is probably now we have a 40%. So that means 12,000. Okay. Now we have another 12,000. Okay. So in terms of the number, we got how many? 6 times 35. Okay. So among the 10,000 students, children, we have 35,000 children lives in the family with owing home. Okay. So so in terms of the children, so this is a family level. So family level, the percentage is 43%. But the children level, we have 35%. children level. So we get discrepancy. So that means the unequal property sampling is implicit in the sense that if you use children, right? If you use children to select a sample, then we are actually oversampling, overrepresenting the family with many children. You know what I mean? Right? Because if you select the sample among the children, right? Then the family with or single children will be less represented. Okay. I mean, if you let's make a real simple example. So suppose we have only two family and select children, one children. Then the probability of selecting a family is not equal, right? So we overrepresent the family with many children. So that means the unequal probability sampling is implicit because this probability, so the selection probability is what? 1/3 and 2/3. If you select, right? If you select in terms of using school children as a sampling unit, then the family in the selection probability for family will be different, unequal, due to the unequal distribution of the children. Right. So that is kind of so that is actually, this area is sometimes called the length bias. Length bias sampling. So basically, if you want to select a sample, but the sample, okay, so here's an example. Suppose you have a different size of farms, and you just randomly select one farm by throwing a point at random. Okay, so you like you're throwing a throwing a dot. I mean, right? Dot. Then the bigger, right? The more likely to be selected. Right? If you just select one point, and then the bigger one. So if the farm is very small, then the chance will be low. So that is one example of the length bias sampling or area bias sampling. Like suppose you do survey in a shopping mall. Okay, you just randomly select people in the shopping mall and ask questions. How often do you come to shopping, right? Something like that. Then the more frequent, right? The person with, so that's a typical example of the selection bias. I mean, the length bias sampling, because those who come to the shopping mall more frequently will be more likely to be selected. So that is another example. Anyway, so that means we need to take into account of this size information in order to correct the bias. Otherwise, you get bias sample. Here's one really popular technique, PPS sampling. M1 to Mn be known characteristics of the population element such that, so this is a size measure, Mk. So Mi is the called measure of size. Example of measure of size include the size of farm, number of employees in a company, and acreage of counties. We wish to select a sample with a selection property proportional to Mi. If the sample size is equal to 1, so NRI, for example, in a CSS in NRI, we also use this kind of sampling, select with this property proportional to size. If the sample size is equal to 1, then it's an easy job to select a sample with a property proportional to MI. Right? Like this. Like this. Here we already have a sampling, right? Proportional to size. Sample size 1, no problem, because we know the total. Then you can just do create a proportion, right? And just so then select one element easy. So using that idea, we can actually do independent selection. So the proper PPS sampling idea is use an independent. So that means independent means that here with replacement. So independent means with replacement sampling. Because we select with replacement, selection in the first row does not have any effect on the second row. So then it becomes independent. So it's with replacement sampling in the sense that once thrown, all elements replaced into the population so that all the n elements participate in each row. So why we use with replacement sampling, first of all? Well, it's easy, right? So the pro is that easy to implement and investigate its properties because it becomes independent. So then we know we can apply the theory under the IID setup eventually. But con is that it may be inefficient because you end up obtaining duplication in the sample. So that creates the inefficiency, right? Why you select the same person, right? Ask a same question. So that's a little bit unattractive. So anyway, at least it's a good start for understanding unequal property sampling. Okay, so through probability. So there's the through property is not equal to selection property. Well, if n equal to 1, through property is equal to pi I. Okay, so if the sample size is equal to 1, then it's essentially this in first order inclusion property. So it's by definition is the property of selecting a unit I for a single row. Okay, such that pi summation over n 1 to n isolation is equal to 1. Okay, and because on the with replacement sampling, so with replacement, right? The row property remains the same, right? And if we have a measurable size, then a pi can be constructed this way. Just mi. So pk is mk divided by the total, right? Total of MI. Okay. In general, draw property is not the inclusion property. So I'm going to introduce another notation. AI. AI is the index of the element, index. So we have a like a 1, 2, capital N, right? And we select one. First draw. So first draw, we suppose we select, we obtain one element which is say 5. Then A1 is 5. Okay. So that is the basically the index. So so AK is basically 1, 2, capital N, right? With the property P1 with the property P2 with the property Pn. Right? By the, so this is definition. This basically you can understand this way. So then now let's compute the pi k, which is the first order. So this is the first order inclusion property, right? Property of, so this is the definition. The property that I is in the final sample, k is in the final sample. So this property is 1 minus p not equal to a. And then because of the independence, we have this. So unit k is not selected n times. So then you get it. So this is the basically the relationship between pi k and pk, right? So then if you check n equal to 1, then we actually have pi k equal to pk, right? And then if you do apply Taylor expansion, okay, if you do Taylor expansion, then you can get something like, right? So if you do I guess what I did was like this. So if I use this formula, this is essentially Taylor expansion, then we obtain this, right? So this is a kind of approximation. And so you get this. You get this. Not exactly equal, but approximate. Okay. Let's move on. So now let's move on to the sampling. I mean the estimation. So now you are interested in estimating the population total, which is y here. And here's basically this is already so in the very first example, right? Very first example here, how did I compute the estimator? Right? This is a Hurwitz-Thompson estimator with a sample size 1, right? And so basically we use a Hurwitz-Thompson estimator of sample size 1, and then there's no problem, right? N equal to 1, we know how to compute the Hurwitz-Thompson estimator already, which is this one. And you can see, actually, you can see that this is a random variable, right? This is random variable. So you can write it this way. Another way of writing this way is no, not really. Sorry. Okay. Not this is not sorry. Let me back up. A1 equal to K K K divided by K. This is actually correct. So another way of writing this formula in a single equation is this. Y hat is so because what is A, right? So A is this one. A is A. So we have a single draw. So A1, right? First A1 equal to either 1, 2 through N. So this is basically another way of writing. So A1 could be 1 or 2, right? So then we at each event we just use this. And then if you take the expectation, the only random variable is A, small a1, right? And so what is the expected value of AI, A1 equal to K? That is a PK. Why? Because this is what we start with, right? This is this one. So we use that. That means we can actually obtain PK or K divided by PK equal to summation. Okay, so you get this. Now, so n equal to 1, no problem. Now we want to apply to n greater than 1, right? So for n greater than 1, good news is that we actually have an independent draw. Independent draw. So that means we can actually apply IID type result. So the width sampling makes the population unchanged after each draw. So for each draw, we obtain one y hat from the probability distribution in the previous page. And then we can basically obtain n of them. Okay, so we basically we obtain, we draw one and compute y hat, and draw another one, compute another y hat. Okay, something like that. So basically, we repeat that n times and take the average. That is basically the idea. So, so basically, this is what you want to propose. So basically, the final estimator is a sample mean of the Zi, where Ci is what? Ci is basically this guy. Okay. So this is a little bit confusing, but if you do it, one by one, that's not really difficult. So, case draw, okay. Well, actually, let's write it I straw, because we use K here. So for the I straw, right? For I straw, we observe AI, small AI, right? So that is the index selected from I straw. So AI is random. So this AI is random, which is basically this one, right? You have only one. So this event is equal to one at only one place, right? So that means you have this. And we already know that this is actually expectation unbiased. And the variance is this one, because of the probability distribution. So use that and use IID. So this is really nice, right? IID. So this with replacement sampling creates IID random variable and IID random variable. Okay. With this distribution. Okay. So then you can actually obtain of the final estimator as the sample mean. So under the IID sample, right? The sample mean is the best linear whatever estimator, right? Unbiased estimator. So that is basically this one. So it has very attractive properties. So that is Hansen-Horowitz estimator. So Hansen is Maurice Hansen. Did I talk about Hansen, Maurice Hansen in the first day? No? Okay. So Maurice Hansen is really is an innovator. So he's a kind of George Neumann, right? So George Neumann is is a professor at UC Berkeley, right? He's a professor and developed the randomization approach. And then Maurice Hansen was a statistician at Census Bureau at that time. And he was very impressed by this paper, And then he wanted to implement it at Census Bureau. So he's kind of a founder. I mean, he's the actual person who implemented the survey sampling, design and estimation at Bureau of Census. So he's a kind of a very innovator, pioneer in survey sampling. So one of the but he's not really strong in mathematics. His original background is accounting or something. So he hired some statisticians epilogue sentence, and they work together. So Hansen was more, no, uh, Horowitz is more, he's strong in theory, and Hansen has an idea, good ideas. So they wrote very important papers together, and one of them is this one. That is like a 1943 or 1944 or something like that, long time ago. George Neumann is more like 130, right? 30 something, 5 something. Anyway, so even before the Horvitz-Thompson, right? Horvitz is 1952 or something. So even before Horvitz-Thompson, Hansen Horvitz developed this estimation and design, it's very attractive because you can easily apply the IID. So you can compute you obtain the unbiased estimator, right? So this is unbiased. This is unbiased because ZI, right? Expected value of ZI is equal to Y. And then because this is IID, you can get this, right? So that is the second result. Third one is the variance estimation is easy. That's really attractive property. Why this is true? Well, because this is basically a sample mean of the IID random variable, right? Sample mean of the IID random variable. And what is the variance estimator? How to estimate the variance of the sample mean of the IID random variable? 1 over n s squared, right? Which is exactly this one. So this is actually, this is SG squared, nothing else. And maybe if your sample size is large, then you should get central limit theorem, right? And obtain confidence interval and things like that. So that is a kind of fundamental result in the sense that in the purely design-based approach, you can develop the statistical inference to the with the unequal probability sampling, right? So in that sense, this is very useful. Okay. Yeah. You mean the one over n here, because like it will be like you mean this one here? Or I mean the one text, the one over n of summation of CI. I mean here? Yeah, so okay. It could be written as like summation of 1 over NPI times yi. Summation of no, 1 over like n times pk times y. So that's like npk. So this is the CI is defined to be this one. Just like it seems to me that like I'm trying to make it equivalent to all its Thompson. Okay. In some sense. Right. Actually, I plan that's probably here. Is that so if you okay, so this is let me maybe we can see if you write this way. So this is what we already right. This part is okay. And what is ZK? ZK is summation of I equal to 1 to capital N indicator AI AK equal to I divided by PI, right? So if you plug in to here, and then change the order of summation and redefine, you can get Qi, which is the summation. So Qi is the number of times that unit I is selected in the set. So then that once you write this way, you can, if this guy can be, if how to write this way, right? How to express. So how do you interpret it? As a weighted sum of the yi object in the set. Where so that means weight is actually Qi divided by n times pi. So Qi is the number of times in the sample, and n times pi I is a, as I said, this is kind of close to pi I. I think that is your question. So if, right, if n is really large, right? If n capital N is really large, then duplication, the property of duplication will be small, right? So then maybe this is good enough. Okay. So that's one remark. Another remark is that using this Qi notation, we can express the variance formula, variance estimation formula. What is the variance estimation formula? The variance estimation formula is this guy. The unbiased estimator of the variance of Hansen-Horowitz estimator. Hansen-Horowitz estimator is this, which is 1 over n times s, right? Turns out that it is indeed this way. Why? Because let's investigate this further. Okay. So how to write it? So this guy is what? This guy is equal to y hat Hansen-Horowitz. And then this is yk divided by pk for if ai equal to k. Right? So if ai, so i's row is equal to k, this is this. So then you can essentially let's write it. Well, not exactly true. Let me write it again. So so let me let's do one by one. Okay. Right. And so I guess CI is AI equal to, I guess CI is 2, K equal to 1, 2, capital, and I equal to K, YK divided by pi K, PK. So a lot of, yeah, so sampling has a lot of notation and some tedious algebra. It's not really difficult, but the tedious algebra probably is a hurdle to master this area. So anyway, Let's include it, right? So what I just did is just rewrite the Hansen-Hurwitz variance estimator using the definition of AK, AI. That's it. And now what I wanted to is to observe that even if it looks very complicated, if you look at this carefully, even if you look complicated, the indicator function, the indicator that a everything is zero except only one, right? Everything is zero except for only one place. So that means you can actually move the summation outside. So that is a kind of my point is you can actually move the summation outside and then YK, PK, no different. So can you see this red, right? So this equation looks very weird because this is not generally true. But because the definition of I mean, because our PPS sampling setup, the the event the event of the indicator equal to one occurs only one place. So then it can actually can go outside. Once you do that, then you actually use this is you can exchange the order of summation, right? Over I and K to, and then if you take the summation over I equal to 1 to n, that is basically how much time unit K is selected in the sample, which is QK. So that gives the result. So this is a little bit algebra. Should be easier than 642 type mathematics, right? It's just algebra. But still it's not really trivial in some sense. Anyway, this is what you get. And then so once you are convinced with this result, then you can actually view it as you can write it this way. So basically if this is true, if QIs are only either 0 and 1, that will happen if this is very, very small, right? If the population is really large, then there's a duplication will be so chance of getting duplication is really low. So QI can be either just 1 or 0. So in the sample there will be just 1. So then basically in this case in QI in sample A, QI is all equal to 1. And then this guy is n times pi equal to pi I, and which is 1 over, so 1 over n pi is 1 over pi, which is wi. So then you can get this. Let me. This is yeah. Okay, this is markdown. I'll mark down for PPS sampling. And so if you okay, so this is Canadian workforce data. So the workforce data is company data. So the distribution is really skewed. And if you use the PPS sampling, right? If you use PPS sampling, then you can maybe you can just check. And then this is the computing the draw probability and things like that. So basically, this is based on 10,000 simulation. You can get so this is simple sampling, systematic sampling, PPS sampling. So they are all nearly unbiased. But if you look at the variance, right, PPS sampling is much smaller, which is good news, right? You can use unequal product sampling, PPS sampling, to come up with a much efficient sampling design, which is very good news. So that is basically a key idea. Okay, well, I need to cover Poisson sampling, but we'll do it this Friday. I mean, not Friday, Thursday. Okay, so let's stop here today.